In the last video, I spoke about Hooke's law. Now I am doing it again, but this time we are going to try to establish link between the two equations that were given. This one involves the force and the extension of a spring with the K as the spring constant. Constant which is only the same among identical springs. This other equation with lowercase sigma and epsilon and a new constant E, the Young modulus of elasticity, is the other formula associated with Hooke's law. By just looking at these, it is not so obvious the connection between the variables, and as I observed in the past, the students are finding it hard to reconcile these two by making connections. And that is this follow-up video is all about. Alright, let's make some space first, then we will try to see how they are linked. Alright, there we go. Now imagine we have something here, anything is stationary where we can attach our spring, and this is the spring. And it will be extended here by extension X, our symbol. When a tensile force is applied like that, if the elastic limit is not reached, then this extension varies directly with the force. That's what this equation is saying anyway, isn't it? Now, imagine that we have another spring here, and these two springs are connected with some kind of a material here. But note that this material will be assumed to have negligible mass, okay? For the purpose of seeing what happens to the spring constant of the system of two springs. Okay, so if we apply the same amount of force here, that force will be distributed between these two. Half acting here and half on the other. This same force as before will then extend each spring by just half of the original extension X. The spring constant is this for each, and that having half of the force means half extension. Alright? Now, how about we increase the number of identical springs? Let's put an area here. This part, we have another spring, and here also. And again, these ends of the springs are connected to a material with negligible mass or weight. If we exert a force perpendicular to this area, we can see that each of these four springs now should be experiencing a quarter of that original force. A quarter of the force leads to a quarter of the original extension, because the K still holds for each spring. However, for the entire system, or say the material itself, imagine that each spring represents force on particles of materials and changes in their separation distance. The system of springs or our material will have different value of K because of changes in X, which we can see here, alright, as inversely proportional to the area. Alright, now let's try to see other dimensions. Our single spring here, again, with this original length, extended to a distance x here when a force is applied on its end, like that. What is going to happen to the extension x if the spring's length, the original or the initial length is changed? Let's erase these ones, okay? Alright, changing the length is like having an additional spring here at the end of the first spring. The length is longer this time. And that if we apply the same amount of force here, Newton's third law will tell us that each part will actually be experiencing the same amount of force. Assuming that the spring has weight or the mass that is negligible, we can say that our first spring is experiencing the same amount of force as the second spring. Because of this same amount, extends a distance of x each. X here, same extension here. So the extension is now double for the same amount of force as an effect of using two springs, or equivalently, making the material longer. The longer the material, the longer the extension for a given force applied on it. This relationship. Alright? Okay, to sum up what we found, our K, which is equal to F over X, remember that this K now is the K of the system of springs or on the material. It changes because of the new extensions we observe. And this extension X is inversely proportional to the area A. This. And directly proportional to the L or the initial or original length of the material. And if we are to plot values of this F over X or the K against this ratio A over L, we expect a rising straight line like this one, alright, this graph. Now, let's rewrite this relationship into an equation. The quantity K or the F over X equals a constant of proportionality, say M, area divided by initial length. This M is the proportionality constant and can be determined here in this graph by taking the gradient or slope. If you're going to do a rearrangement here by cross multiplying, bringing the A here and X here, and we should get F over A equals M, X divided by L, after moving the variables. Okay, now, this looks familiar already, isn't it? It's a bit similar now as in the equations I presented in the last video. These ones here, see? This F over A is the stress, which is represented by this symbol sigma, and this X over L is the strain, which is represented by this epsilon. By inspection, it is easy to see that this E is in fact our M in this equation, isn't it? Which represents the Young modulus of elasticity. Okay, so that's it. We started with the first equation showing Hooke's law, this, for a spring. Then we model materials with particles in it, acting as if they are spring. And we got this second equation of Hooke's law. That's how these are linked. It is now obvious that E, or the Young modulus, is the constant for a given material, regardless of the shape and size. And for the spring constant, constant only in one specific spring. When you change the dimensions, that K of spring will also change. Alright guys, bye.